And then let's see if the recording is starting automatically. It seems it's
it is
check
for
here.
I think hand job.
Here?
It's not mine.
I thought you used in your cup.
Yeah.
Record.
Some cream.
Okay. On.
It's recorded. But here, like, it doesn't matter that it's stuck.
Image. I don't know why. But try share.
Where? Paula.
It's me.
You can see us?
Paula. Are we stuck?
I can't see anything.
No, because probably it only opened in a few minutes. Yeah.
We have Kevin.
There is also Kevin. Yes.
It's one of the attendees, I guess. Swedish.
I can't. You see, it is
Remember Kevin?
black.
Number one.
I don't know if you know.
Now?
Now, okay. I can see the slides.
We are moving. Oh, perfect.
I can see only the slides, not
So good morning, everyone. My name is Marian. I work as a senior project manager for EUPC. I welcome you all to the Merlin webinar, where we're going to look at developing innovative solution for multi-layer packaging. We're going to start with the EUPC introduction by Managing Director Bernard Marx. Then we're going to move to Francisco from Itene, that's going to present overall Merlin project. Then we're going to have Marianne from Ionica, that's going to talk about the polymerization of PET. We're going to go back to Francisco and very interesting topic on delamination of non-metallized flexible packaging. And this part we're going to finish with Chiara from University of Bologna of the delamination of metallized flexible packaging. In case there are any questions from the audience, our speakers will be more than happy to answer any questions. After that, we're going to close the webinar from EUPC offices in Brussels. Bernard, I leave it up to you.
Yes, very good morning, everybody. I hope you can hear and see us well. We are hosting this webinar here today from the EUPC offices in Brussels. Just a quick introduction. I have a very long background in plastic converting and plastic recycling. You see me here on the picture sitting in front of post-consumer recyclate bills and sitting on a 3D printed bench, which is made out of 100% post-consumer recyclate. EUPC, in a few words, is the umbrella organization of the plastic converting industry. We are representing around 50,000 companies in Europe. Many of them are SMEs and family owned. The count is around 1.6 million FTEs on direct employment, and if we look in our supply chain, we're more than double than that. The joint turnover of the industry is around 300 billion euros, which makes us one of the larger industry chains in Europe. To make it clear, our members convert plastic raw materials into products, and they are used in all industrial sectors, both in Europe, and some of our members are also supplying it to the global economies. Less known is that many converters also operate integrated recycling facilities and have invested in mechanical recycling facilities. Estimated 65% of today's installed capacity is owned by the converting industry. We have a few topics, main topics: global warming and, of course, plastic bashing. You find plastic news in the social media every day, and not always in a positive way. We have a lot of opportunities and challenges ahead. Decarbonization, circularity, and climate change are basically the three words we're using next to innovation. Just a few slides on what we have done already, for example, on climate change. Last year, we had a big summit, or meanwhile, October 22, a large summit in Lisbon with more than 1,100 people from the industry from a global part, South America, Africa, and Europe, where we talked about a lot of things. I was chairing the climate change discussion. And on the side next to me, you see that we're standing on a very interesting boat where we had 150 sustainability managers gathered on a boat. And it's this boat, it's a Portuguese white fleet ship, which is restored and does eco voyages. It's a partner of my foundation, Waste Free Ocean. And they are doing, among others, microplastic research for us, but also for the United Nations. We have a lot of challenges, and without going through the whole slide, just a small list of all the topics we've been dealing with last year, and most of them will follow us also throughout this year and next year. A lot of legislation coming up, and we also have things to do about, let's say, waste shipments and this kind of thing, because we need to get materials to the recycling facilities. We have leadership and expertise in the field of regulatory aspects, not only in the packaging and packaging waste, but also in other markets. We lead the efforts of the assessments on the EU level. And for us, projects like Merlin, where we are speaking yesterday and today, they're a great added value for our industry because they can support the converting industry commitment to foster cross-sectoral circularity and sustainability. And just to name it again, the plastic converters are at the heart of the EU industry, and our customers, brand owners and retailers are key to complete the transition into circularity. So proactive transformation to support converters and converters recyclers towards further circularity and net zero is one of our key priorities. We are fighting greenwashing because we see a lot of wrong claims by users in the market. Plastic packets has a lot of advantages in comparison to alternative materials, but we see that people are choosing different ones, probably on emotion and not so much on ratio. So we are still working in an increased level on the LCAs to also show the carbon benefits of packaging and plastic in general. And of course, there are issues where we need to redesign products. I've looked at the Merlin challenges, and they are very good. There are around 3 million tons of multi-layer packaging, and I'm very curious to see where, at the end of the project, we are landing. There are a lot of challenges on the website, so I'm curious to see that. On the other hand, if we look at what we do, we're not in charge of waste management, which was okay in a linear economy, but in a circular economy, we need to take more action and get on top of availability of high quality recyclates. And this will become a challenge in all plastic applications. We have introduced a few activities. One of them is more our industry data collection, post-consumer recyclates material, where Marianne, who you just saw, is in charge. We have introduced PolySet, which is an umbrella compliance scheme for harmonized auditing and certification on recycled content. We are working a lot on SEN standards with a number of technical committees in many different aspects. And it's very important for us as an industry to work much more on these ones, especially when we have to introduce recycled content in all the activities. A few last ones. Some of the topics, of course, on the top of our priority is the discussion around microplastic. Together with the producers of virgin material, we have created the Operation Clean Sweep, where we asked the converting industry to keep their houses clean and to prevent losses of pellets. The reason for that is that the losses of pellets is one of the largest sources of primary microplastic. In recent weeks, there was a spillage of the Spanish coast, where you see that only a few bags of material can create a lot of environmental damage. So it's also part of our responsibility to prevent that. The good thing about the upcoming legislation is that also the logistic companies now are involved and have to take responsibility to prevent losses. The last one on recycling. There are two types of recycling, mechanical and chemical recycling. As already stated, the converting industry is predominantly active in mechanical recycling, but for some applications, we need chemical recycling solutions. And I think in the Merlin project, some of those solutions will be brought up. And if you look at what we already know as mandatory content in only 3 or 4 legislation, it's going to be a very hard challenge to get the high quality recyclates back to the converting industry. A recent publication, McKinsey also predicted that we will have insufficient quality material coming up in the years to come. And we may have to think about urban mining or the other alternatives to get more access to materials. So I finished the one. The plastic value chain is in transition towards more circularity, and I wish you all a successful webinar. Thank you very much. And I pass on to Francisco. Not too bad.
Okay, thank you very much to UPC for your nice introduction. I'm Francisco Sanchez from ITENE, and I'm going to present the overall of the project Merlin. In that case, in this first slide, you can see the. Okay, I think it's a problem with the presentation. Let me a moment to check. Okay. Okay, now I think it's okay. Okay. As I commenting, this is the first slide of the presentation. The main Merlin is the objective is increasing the quality of and rate of the multi-layer packaging recycling waste. This is a project that takes part of the call from 2020, namely improving the sorting, separation, and recycling of composite and multi-layer materials. The time of the project is from 2021 to 2024. I mean, this year the project ends, and the budget was 4.9 million euros. They are involved in this project 14 partners from 7 countries, as you can see in the image of the of the slide, and you can see that there are from different sectors of the plastic recycling, sorting, delamination, service provider, and packaging industry. And just to finish, this Merlin is a proposal that is a RIA, a research and innovation action. You can see in this image where are the different partners of the project. There are different sectors, as you can see, and there are from different countries like Germany, Belgium, Croatia, Spain, France, the Netherlands, and Italy. This is the summary of Merlin project. The problem that we want to solve is the big quantity of post-consumer packaging waste that is generated in the European Union, 70.8 million of tons of this type of material, and only 42% are recycling right now. This represents a very high economic impact, 10,605 million of euros, and environmental impact that is also a big quantity of millions of tons of CO2. In order to increase this percentage of this yield of recycling rate, we want to work in this part of the project in the valorization of different fractions of plastic packaging. In that case, and you can see in the slide, there are the rigid multilayer packaging, the flexible packaging, and the metallized flexible packaging. Why multilayer packaging? There are different reasons in order to be focused in this type of material. The type of packaging is widely used due to its high performance at 17% of packaging. Its identification in plant is very complex and inaccurate, and we need to separate in the different flows in order to have a better yield of recycling in the next steps of the process. There are different natures of the layers, for example, PET, PE, and also there are, for example, different layers of aluminum in that case that represents a very difficult process in order to be recycling. And finally, the delamination is suitable for certain very specific structures, and we want to improve this recycling in order to increase the recycling of a bigger quantity of material and in a mix of different types of material and structures. The main objective of Merlin is the development of new sorting, delamination, and recycling processes for both flexible and rigid multilayer post-consumer packaging in order to produce new packaging solutions. You can see in the image of the right of the slide the different processes that we develop in the project. In gray, you can see the sorting, packaging, and identification. It's followed by the delamination, separation, and recovery processes that it's the main focus of this presentation. You can see that we work in selective depolymerisation, that it's a task led by Jonica from the Netherlands. Also, we work in the delamination of flexible packaging, that is a task led by Itene from Spain. And finally, the solvent-based delamination for metallized flexible packaging, that it's led by the University of Bologna. The next step for this process, in order to close the loop, is the recycling, recovery, and reprocessing of the material recovered from the previous step, and finally, the validation of the upcycling packaging. This is the same scheme, but with more detail of the different phases. We can be focused in the part of the center of the slide, and as you can see, they are represented the different tasks that we develop in the project regarding the rigid multilayer non-metallized with the catalytic depolymerization and depolymerization with supercritical fluids, the flexible multilayer non-metallized with also the supercritical fluids solvent separation and the green versus traditional solvents, and finally the flexible multilayer metallized with the solvent-based separation. And also we have several transversal tasks, as you can see, for example, of the food contact safety analysis, circular by design, recycling cycle analysis, or knowledge generation in order to have a bigger project and be focused in another transversal tasks that are also very interesting in order to valorize this type of material. In this slide, you can see the main pillars, that we are focusing in the project. First one, expand the emerging smart waste management sector, introducing smart technologies in sorting plants in order to separate the different flows in the sorting plant, the delamination of multilayer structures in packaging, rigid, flexible, and metallized flexible multilayer. The main pillar of the project, I think, is the develop. Basically, the main objective of the project is develop and promote new sorting, delamination, recycling, and validation processes for the different structures that we valorize in the project. And finally, improve the properties of the recovered materials with, for example, additivation in order to improve these properties or characteristics in order to be very accurate for the final upcycling, and finally produce new prototypes in order to close the loop of the recycling processes. We have also clustering opportunities. For example, we are looking for industry inputs on Merlin developments, the validation of how Merlin is in accordance with the European legislation, inputs from policymakers on where legislation is heading in the future, the extrapolation of the value chains for another type of plastic waste, and finally adding new members to the advisory board that we have several meetings, some months in a year, in order to have the feedback from another companies and another possible partners for the future, in order to be aligned with the interest from the companies in this sector. Just to finish, the contact information, you can see the different social media that we have in the project. That you want to have more information about the project, you can check all of these resources. And that's all from my side. Now is the turn of Ionica in order to explain the process of the polymerization of PET. So I give the floor to Maria in order to explain this presentation. Thank you too much.
Okay, so welcome to Ionica's part in this webinar. Sorry.
Here, screen, the screen, and then your presentation.
Okay, sorry, I will start over. So welcome to Ionica's part of this Merlin webinar. I will be introducing Ionica to you, and I will also explain what we have done in the Merlin project so far. If the slides will go. Sorry. So I will follow this table of content in the next few slides. So let's just immediately start with a bit of background on Ionica. We are a Dutch scale-up company. We started as a spin-off from the Technical University in Eindhoven back in 2009. And ever since, we're specialized in the chemical depolymerization of PET, which we can do with our own catalyst that we have developed. And the combination of this catalyst and a very sorry?
Go on.
Oh, okay. And a very in-depth purification process results in the fact that Ionica can produce high-quality PET monomer. So in the last few years, the team has almost doubled, by which I just want to emphasize that the company is growing and developing a lot lately. Also in terms of patent families, Ionica grew a lot since when we started in 2009 and now. From 7 patent families, we're now up to 19. and patents and IP protection is very important to Ionica, since we are a company that is focusing on licensing. Eventually, our technology will be licensed all over the world, hopefully. So we focus on selling licenses, but we also have a chemical depolymerization plant in Geleen, which you can see with the blue pin that's in the map of the Netherlands. It's in the city of Geleen. So this is just briefly a bit more on the history. You can see Ionica was founded. We started with filing the first patents, but then in the rest of the slide, you can see that we won some awards that were very important to us and helped us developing. And in the end, now we have some partnerships. So in 2018, partnership with Unilever, Inorama, and Coca-Cola. But last year, KTS came on board to help us to really license the technology. And of course, legislation is also already mentioned, and that's also in this timeline, because it's of course very important to Ionica. So the objective for Ionica, so what is Ionica really doing? What are we focused on? Well, that is to recycle the unrecyclable PET waste. So chemical recycling and mechanical recycling was already mentioned in the introduction by EUPC. And we take unrecyclable PET waste, so it's not suitable for mechanical recycling, and we will do this waste treatment in a chemical process. And by doing so, we contribute to a closed loop for PET plastics. So now a bit more in depth on the technology that Ionica uses for PET upcycling. The few steps that we do to go from low quality material to very pure material is that we start with shredded colored PET waste. And this PET waste can have some impurities like other flakes, other polymeric flakes, or maybe even metal flakes in this feedstock, in this PET, the PET mix that we use. Then we go to our Ionica process, which means that we put solvent and our catalyst that I mentioned in the first slide, our smart magnetic catalyst, to allow for the depolymerization. So the PET will be fully depolymerized. And then in step 3, we need to reclaim our catalyst, because we want to reuse this again and again and again in our process. And then step 4 is some more purification step to make sure that the monomer that we obtain is very pure and can be used as a virgin raw material. And that's then step 4. So the Ionica process, so what just was one beaker in the diagram of the previous slide, is actually the glycolysis route that Ionica is following. So there's multiple ways to chemically recycle PET, or to fully break down PET into its constituent parts. Ionica opted for glycolysis because it is a relatively simple process with also the mildest process conditions. It doesn't break the ester bond, and therefore it's less energy intense and makes it a bit more cost and eco-attractive. You can see in the diagram that actually the glycolysis is the shortest route. And the shortest route produces one final product, and that's BHET. That makes the CAPEX investment a bit lower. But on the other hand, BHET is also a bit the disadvantage of glycolysis, because this is a new monomer. And that means that we need to make sure we are allowed to make it. So we need to work a bit on the legislation as well for this new monomer that we then bring on the market. So that was all a bit on Ionica and what we're already doing. And actually now in the next few slides, I will focus more on what we did in the Merlin project and what we did with rigid multilayer packaging materials. So in the slide, you see a multilayer plastic packaging with an EVOH polymeric layer in the middle. And within the project, we established that the rigid multilayer packaging very commonly has this EVOH middle layer sandwiched between other polymeric layers to make sure that oxygen, to function as an oxygen barrier. So to make sure that no oxygen penetrates the food packaging, and therefore the shelf life of the food is increased. Within this Merlin project, Ionica has developed a pretreatment step so that this EVOH polymer can be removed, and then the material actually delaminates. And with this EVOH removal pretreatment step, we actually are leveraging on the core process, because we have a new pretreatment step, but all the other steps that I've shown in the previous slides for the glycolysis are exactly the same. So it's just one additional add-on. So this is a slide just specifically on that pretreatment step, the delamination step. We take the multilayer flake with solvent and we basically put it in a pot and we mix it, and we need to put some more heat such that the EVOH oxygen barrier starts to dissolve. And then this middle layer is dissolving, so a polyolefin layer and a PET layer are separated. And that's actually the three different streams that will come out of this pretreatment. There will be a high density fraction, which is the PET. There will be a low density fraction, which is the polyolefin. And then there's the solvent with EVOH dissolved into it. And of course, we need to work on solvent recovery. We do a separation step of the EVOH and the solvent and use the solvent again. And this is just an image to show you what it looks like in a beaker glass. And if you look very carefully, you see a polymeric blob floating around on the in the beaker. You see that it's floating, so you can clearly see that the polyolefin layer has delaminated and collected at the top, and the PET that is now delaminated and clean and ready to be used in Ionica's depolymerization process is all collected on the bottom of the beaker. So then the total process for multilayer recycling looks like this. So you recognize the 4 pots that are already Ionica's core process with this multilayer pretreatment step in front of it. And this is then how the whole process would look like. These are some photos of samples of all these separate steps that we made material for the next consortium partner. And these photos are actually the samples that were taken during this trial. So 80 kilos of BHAT of our monomer was successfully produced for work package 3 to use and test on quality. And these samples that you see are actually the samples that were taken during the trial of making this material. So in the top right corner, you see the white powder, which is our very clean monomer that will be polymerized again by the next partner in the project. So those were my slides. So now I'd like to give the floor back to Francisco for the next presentation.
Okay. Okay, thank you very much. We are going to move now to the presentation of the delamination of multilayer film packaging using green solvent-based processes. This is the table of contents. We want to start with the presentation of my company, ITN, the objective, the theoretical form of the process, and finally the efficiency results and critical parameters. Let me start just introducing ITN. The objective of this technological center located in Spain is generate knowledge and technology to bind together a safer and more sustainability future throughout for many areas of work. As you can see in the image, materials, packaging safety and environmental monitoring technologies, and finally transport, logistics, and mobility. You can see in this slide the different technologies that we work in the technological center related to, for example, recycling technologies and bioprocesses like industrial biotechnology, and different materials and packaging technologies and other regarding the different sectors of the recycling of materials by analysis and biodetection of packaging engineering. In this slide, you can see the different sectors that we work, raw materials, packaging, agriculture, and you can see in the slide a lot of different sectors. And finally, just to finish, this is the different R&D project that we work in the different years. And for example, in the last year, we were involved in more than 100 projects regarding this type of technologies. And you can see that right now we are almost 200 professionals in the center. And now let me move to the objective of this task, that is to develop a non-metallized field delamination using traditional solvents like methanol or ethanol and green solvents. In that case, in this project, we are focusing the supercritical CO2 in order to delaminate the different layers of the multi-layer packaging. We are also working in the combination of both in order to increase the delamination yield of the process. You can see in this image the main scheme of the process. Just to start, we analyze the Hansen solubility parameters in order to check what are the best solvents in order to delaminate the different multi-layer packaging that we have in our facilities. The next step is the characterization of the multi-layer packaging in order to know what is the structure and how to focus in the delamination of the different structures, the operational condition definition in order to optimize the different characteristics of the process, like temperature, pressure, and the flow of CO2. And also, for example, the use of co-solvents, and finally, the layer recovery in order to evaluate the rate of delamination of the process. We are focused right now at the beginning of this presentation in the Hansen solubility parameters analysis. This is a scheme of the process. We select different solvents in order to evaluate, for example, if the adhesive can be soluble or insoluble in the different solvent. With this information, just with yes or no soluble in this different solvent, we can perform an analysis with a software in order to check if the different solvents, not only the solvent that we analyze in the lab, but another that we have typified in the software are a good solvent or bad solvents in order to do the performing of the trial in the lab. You can see in the image that if the sphere of the solvent is inside of the polymer sphere, it's a good solvent, and is back of the sphere is a bad solvent. The next step of the valorization of the process is the characterization. You can see two of the techniques that we use in the project. For example, the differential scanning calorimeter in order to evaluate the thermal analysis of the material in order to understand the properties of the material. For example, with this equipment, we have the possibility to evaluate the different peaks of the melting points and the characterization points that are very representative of the different polymers that take part of the different structures of the market. And we have another technique that represents that is the Fourier transform infrared spectrophotometry that is basically called by FTIR. And basically, we have the possibility to analyze the layer of the different multi-layer packaging, just checking if the outside and inside layer are from one polymer or another polymer, because each polymer have a different spectrum, and we can check it. This is, for example, one of the samples that we analyze during the project. We have in the center of the slide the analysis by DSC, and we have the different temperatures of crystallization and melting points. And finally, in in the left of the slide, you can see the FTIR with the spectra of the external layer and internal layer. You can see that the external layer is, in that case, polypropylene, and the internal layer it's polyethylene. So the final structure of this sample, for example, it's PP, EVO, and PE. The next step of this process is the operational condition definition. You can see in this image that we use this supercritical CO2. The condition of supercritical CO2, it's upper of this condition of the critical point, that is a pressure of 74 bars and a temperature of 32 degrees. And we have, with this supercritical condition, the best properties that have the gas and the best properties that have the liquid. In that case, the best diffusion of the gas and the best dissolution of the liquid. And with this very specific condition, we have the possibility to have a high solubilization capacity in order to separate the different layers of the multi-layer material. The methodology, as I commented, is the conditioning of the material, the development of the processes in order to separate the different layers, and finally, the final stage of this process, it will be the industrial scale-up of these processes. This is the scheme of the supercritical CO2 plant. As you can see, we can start with the bottle of CO2. When the bottle is open, he arrives to the mass flow control in order to check if the flow is constant and homogeneous, and this flow of supercritical CO2 arrives to a pump in order to push the CO2 into the plant. In that point, we have the connection with the co-solvent delivery system in order to mix the CO2 with the co-solvent that can improve the yield of the lamination of the process. And finally, we have two reactors where inside we can introduce the scraps of the multi-layer packaging in order to separate the different layers of the structure packaging. This is a photo of the supercritical CO2 plant in ITN facilities, and it represents in another photo more small the co-solvent equipment that we use in order to introduce the co-solvent into the plant. And we can see also the different modification in the packaging when we modify the different condition of the supercritical CO2 plant, like the time, the pressure, and the temperature. And just to finish, I want to talk about the layer recovery. Just I want to comment that in the Merlin project, we optimize different condition of the process. Regarding the supercritical CO2, we improve the pressure, temperature, and flow of CO2. And regarding the co-solvent, we optimize the co-solvent and the quantity of flow co-solvent that we introduce in the plant. And you can see in the final image one example of a sample of multi-layer film packaging that we separate the different scrap. In that case, is PET and PE in two independent flows that can be improved with a next recycling in order to obtain the final prototypes of the project, in order to close the loop of the valorization of this type of structures. And that's all from my side. In that case, I give the floor to Chiara in order to explain another investigation of the project. Thank you.
Good morning, everyone. I'm Chiara from the University of Bologna.
And I work in the group of sustainable chemistry of the Department of Chemistry Giacomo Ciamician in Ravenna, a very nice city in the north part of Italy, full of art and nice landscape, in which we, as a group, we are trying to work on different aspects of the sustainable chemistry. That is a very huge topic. And actually, we are trying to face this huge topic by taking into account different parameters. For example, we try to develop new processes by using and design benign chemicals, like, for example, green solvents. We try to combine different approaches and technologies for facing challenges in the field of sustainable chemistry, like, for example, microbial technologies and thermochemical technologies. We try to reduce the impacts of our processes by taking into account each phases of the process, so through tools like life cycle assessment. We try to reduce the use of natural resources, or we try to produce chemicals and polymers that are not dangerous for the environment. And lastly, we try to develop processes that make use of waste in the framework of circular economy. And specifically in this topic, we have been recently involved in two projects. The first one, that is a LIFE project named Cross Life, is based on the use of sewage sludge to produce bioplastics. And the second one is the Merlin project, so from plastic waste to new plastic material. In the Merlin project, we are involved in the separation of polymers and aluminium from flexible metallized packaging. And actually, this is a quite challenging topic because, first of all, the variety of flexible metallized packaging is huge. For example, as you can see from the slide, in this category, we can have a aseptic carton for food and beverage made by paper. The majority of the material is paper, but also many layers of plastic, typically polyethylene, and also aluminium. In this category, we have also material in which we can find a thick layer of aluminium in between, like a sandwich of different polymeric layer with different composition, like, for example, in the coffee bags, in which we can find layers of PET and also of PE. And lastly, we can have also packaging for food composed by polyolefins, but in this case, a really thin layer of aluminium. So a quite complicated composition for this kind of materials. In terms of end of lives, the management can be different according to the country, but for example, like in the case of Italy, according also to the region. For example, the flexible metallized packaging, in which paper is the main material, it is common to collect this kind of waste in the paper separate collection, which is the destiny of this kind of materials. They are sent to paper mill, where they are subjected to an hydropulping processes for paper recovery. And then the residues composed by polyethylene and aluminium is typically sent to incineration for energy recovery or landfill. On the other hand, we have also material without paper, and in this case, it is quite common to collect them in the plastic separate collection. And also in this case, the material is typically sent to incineration for energy recovery or landfill. Our role in the Merlin project is to find alternative solutions to this kind of end-of-life strategies, and specifically our aim is to recover material. So to not produce energy, to not landfill anything, but to recover not only paper, but also polymers and aluminium. To achieve this goal, we developed two approaches. The first one is based on green solvents or bio-based solvents. You can see here in the slide, there is the structure of three of them. The first one is called cyclopentyl methyl ether. It is an ether compound obtained from renewable resources. The second one, 2-methyl tetrahydrofuran, is also a bio-based compound, and it is also an ether compound. And the last one is biodiesel, that is known as biofuel, but can be also used as a bio-based solvent. So in the slide, you can see the scheme of our approach. For example, targeted design on flexible metallized packaging containing paper. After a first separation of paper and polymer and aluminium, we focus on this second part, so polymer and aluminium, that are put in contact with the selected solvent. So we have a step of solubilization of the polymer with a material loading that is typical below of 2% and 100 degrees of temperature for 1 hour of mixture. Under this condition, we get the solubilization of PE. We can recover aluminium by filtration, and then we can at the end recover LDPE by or solvent evaporation or by the addition of an anti-solvent. In terms of quality of the material that can be recovered, we have a very high mass recovery for both the components, so for both aluminium and the polymer. Both of them as minimal organic residues or polymeric in the case of aluminium or in terms of solvent on LDPE. And both of them as a very high quality because aluminium is not oxidized and the polymer has a very good mechanical properties. The critical point of this approach is surely related to the fact that we cannot operate with higher material loading, so below 2%, and this parameter compromise, let's say, the energy consumption of the entire process, because for heating and recovering the solvents, we need to spend a lot of energy. Another negative point or critical point is the fact that these solvents cannot solubilize PP and PET, so they are task-specific for metallized materials that contain polyethylene. This is the reason for which we develop also a second approach in which the delamination of the multilayer material is achieved by the use of aqueous solution of surfactants. In this case, as you can see from the icon in the slides, we aim to use recyclable surfactants, and the tool that we use for recycling our surfactant is the CO2. From the picture, you can see that the first step is the delamination in an aqueous solution with the material loading that is typical below 10% at 100 degrees for 30 minutes. The layers are separated and they have different densities, so they can be collected by density in the vessel in which we produce our delamination procedure. After a washing of the material, we can recover aluminium and the polymer, and also the surfactant by the addition of CO2. In terms of quality, also in this case, the mass recovery is very high, and the material recovery is good since we do not compromise the quality of both aluminium and the polymer. For what concerns the surfactant, just a deepening on the chemistry behind this technology, you have on the left side of the slide the actual surfactant, so the chemical structure that is active in the delamination. You can see that it is an ammonium salt with a long chain carboxylic acid as a counterion. This ionic form is water soluble and it is capable of performing the delamination. When the delamination is completed, we can remove the material, and then simply by adding CO2, bubbling at room temperature and room pressure, we can change the pH of the solution and we can achieve the precipitation of the carboxylic acid, the long chain carboxylic acid, that can be recovered very easily by filtration. The positive factors of our approach is that we can work with a higher material loading than what we develop for the solvent-based protocol. And in this case, we can also achieve a good delamination of different material than PE aluminum one. Like, for example, the material in which we have layers of polyethylene and polyethylene terephthalate. Unfortunately, the complexity of polypropylene and aluminum materials is quite huge. So just in some cases, we can get the lamination of polypropylene, and in some other cases, no. So this protocol is still under development. And I think I have concluded, and I leave, thank you all for the kind attention, and I leave the floor for the final conclusion.
Yeah. So, no. So thank you all. Thank you to all the speakers. I would ask our audience if there are any questions, so they can type in a chat. While you think about your questions, just to remind you that we had a variety of speakers for our webinar today. We started with Bernard Marx, our managing director of EUPC. Francisco presented the overall Merlin project, but not only that, he also talked about the delamination of non-metallic flexible packaging. We also had Marian from Ionica. She talked about the depolymerization of PET. And then our final presentation was Chiara from University of Bologna, and she talked about the lamination of metallized flexible packaging. In case there are no questions, I would say thank you for joining us. I wish you a good day from EUPC, and for entire Merlin consortium, please have a good day, and bye from Brussels for now. Thank you.